Hi people, and welcome to the trigonometry section of the grade 12 mathematics paper 2 May-June 2026 exam. Okay, so we're on question 5, and question 5 says 5.1, given sine A minus B is equal to sine A cos B minus cos A sine B. 5.1.1 says we need to use the formula given to derive a formula for sine A plus B. Okay, I think this is one of the simplest ways they've actually written this question, because before they would say this and is equal to, and then they would expand that. Maybe that was a little confusing, but this is actually a very simple way of presenting this question. So the idea is we're going to use this rule. You know how sine A minus B is equal to sine A times cos B and minus cos A times sine B? We're going to use that to form a formula for sine A plus B. So we're focused on this, sine A plus B. But do you see a problem with this? To use this rule that we have above here, okay? So to use this rule to derive a formula for this has a plus, this has a minus. So how are we supposed to apply the same rule to this? Well, we would have to change this to a minus first. So we can rewrite this as sine, and then we have A. Now, instead of leaving this as plus B, we can change it to take out a minus from this. If you take out a negative, because it's like positive 1, if you take out a common factor of negative 1 from this, then what you multiply to negative 1 to get back to positive 1, you'd multiply by a negative 1. Okay, so we're really just going to take out a minus and say, what do we have to do to get back to the positive B? Well, you need to multiply by a negative B. And now we are ready to go ahead and use this formula. Okay, so just like the formula says, if we have sine and then A, an angle, minus another angle, you must say sine of that first angle. So we're going to do the same thing here. We'll say sine of our first angle is A, and then you need to say cos of your second angle. So their second angle was just a B because they have a minus here. Our minus is here, but our second angle is a negative B. So we must say cos negative B. And then minus in the middle and cos. And we have A, the first angle. Our first angle is also an A, just like this. So we'll just say A. And then sine B. But our second angle is a minus B. So minus B. Okay. And all you have to do is simplify this. So this is simply equal to, you have sine A times cos B. Okay. Cos, but you're going to have to simplify that. You see cos negative B, that the angle is negative. So you can simply just add 360 degrees to this, which would give you cos 360 degrees minus B. If you had to reduce this, this would simply simplify to cos B, because we can see that 360 degrees minus beta, this reduction is in cos's quadrant. Okay, so that just simplifies to cos B. Then minus, and then we have cos A. And what is sine negative B? Again, the angle is negative. Add 360 degrees to it, and you have sine 360 degrees minus B. But you can see that this reduction is in cos's quadrant. Sine is negative in this quadrant. So this would become negative. So multiply by negative sine B. Okay. And finally, just simplify. So this is equal to, we have sine A cos B. And when you say negative cos A times negative sine B, that gives you positive cos A sine B. And that is our answer. Moving on to the next question. The next question, 5.1.2 says, hence, without using a calculator, okay, solve for x in the interval where x is an element of, and we'll go from 0 degrees to 360 degrees if, and this is what they give us. So if square root cos x is equal to all of this. Okay, remember that they used the word hence. So because they used hence, it means it has something to do with the previous question. So they probably, all of this, that looks weird like this, they probably just use this same rule, okay, or this one specifically, because that's what we had to expand, okay, or find a formula for. So let's see the way this is structured. We have a sine, okay, sine, we have cos sine, okay, it's already following it, okay, the compound angle rule for sine. And then we have a 50 degrees plus x, and then 10 degrees minus x, 50 degrees plus x, 10 degrees minus x. Do you see how that perfectly follows? A, B, AB. Okay, so that's the A, that's consistent. That's the B. So yes, they are clearly using this one. Okay, so we can see that that is sine A cos B, and then plus, okay, cos A sine B. Okay, so we can just say this is the square root of 3, and then we have cos x is equal to, and we can just basically simplify that using its identity. Because it follows this, to simplify it, we can just say it's equal to this, sine A plus B. So this is going to be sine, and you can see that the one that would serve as our A, that would be the 50 degrees plus x, because that was the first one. And then this is the B. Okay, see, again, that's A, that's B. So we're just going to have 50 degrees plus x, and then you're saying plus the 10 degrees minus x. Of course, if you add a negative, it stays negative, so we don't really need brackets there. Okay, so this is what we have, and we have square root of 3 cos x is equal to sine, and do you see that positive and negative x, they will just become 0. 50 degrees plus 10 degrees is 60 degrees, which is a special angle. So it means we can find the value of sine 60 degrees. Sine 60 degrees, that its cofunction is cos 30 degrees, which I know is equal to the square root of 3 over 2. You could also just use a calculator for that. So root 3 cos x is equal to square root 3 over 2. And yeah, what did they specifically say? They want us to solve for x, okay? But within this interval from 0 degrees to 360 degrees. Okay, so instead of this being a general solution situation, we're trying to find specific solutions for x within that interval. So to solve for x, you see that you need to get cos x alone first. And so this is what is distracting us. It is multiplying to the cos x. So to get rid of it, you must divide by it. So you'll divide by root 3 on both hand sides. Okay, so if you did that, you can use tip and times. And so this is just going to be cos x is equal to, if you say root 3 over 2 divided by root 3, okay, it's root 3 over 1 since it is, we can write it as a fraction. And then you tip and times, so you're going to swap the numerator with the denominator, and then you change that to a multiplication. So do you see that across we have root 3? Whatever is common across would cancel. And so that leaves us with the 1 over 2. So cos x is equal to 1 over 2. This is what we have, and we need to find the general solution. Okay, so to find the general solution for this equation, we're going to first find our reference angle. Okay, so to find the reference angle of cos x is equal to a half, we're just going to say to find the reference angle, this is equal to, on your calculator, you can simply press, so you're going to take the cos over, we're transposing it. So it becomes the second function of cos. So we'll say shift cos 1 over 2, and we get 60 degrees. So this is 60 degrees, okay? And now we can solve. So cos x is equal to half, which is a positive value. I'm using the table method here. Okay, since cos is positive, we're going to look for the quadrant where cos is positive, which we know is in the first quadrant, okay? Here, where we just have whatever your reference angle is. And then in the fourth quadrant, okay, where cos is positive, and the reduction here is 360 degrees minus theta. Okay, so let's use those. Now we're trying to solve for x. So we're saying x is equal to whatever our reference angle is. And we'll just say that is 60 degrees. And then you would say, of course, you don't really have to say plus k 360 degrees. It's not necessary. And this is why I don't like using this method too much. I like to rely on the graph. Okay. So if you were using the table method, okay, the only one that would work for this interval 0 to 360 degrees would be the 60 degrees. Okay. If you said plus k 360 degrees and you substituted okay, values for k. So the only one would work is where k is equal to 0. Okay, that integer value of 0. So here, what I would actually use, that would be how to use the table method really. Okay, then you could also say, oh, x is equal to 360 degrees minus our reference angle, which is 60 degrees. And so that would give you 300 degrees. Of course, you'd also have plus k 360 degrees if you were using this method. And then the only one that would work would be the one where k is equal to 0 as well. Okay, so you can do that. The method I would just use is simply just the graph. I know what the cos graph looks like. I'll say, okay, this is my cos graph, and I know it looks like this. So where is it equal to a half? I know that it is equal to a half at 60 degrees, okay, because that was the reference angle. And then the next place where it would be equal to a half, you just have to say 360 degrees minus 60 degrees to get that. Okay, because what the cos graph does from here to here, it does the exact same thing from here to here. So if it took 60 degrees for its y value to equal half, then from here, it's also going to take 60 degrees backwards for its y value to hit a half. Okay, so that would just be using the symmetry that we have in our cos graph. Okay, so here I'll just know that this is x is equal to 300 degrees. So this would be our answers. These would be our answers for that interval. Okay, moving on to the next question. Okay, question 5.2 says we need to prove the identity. So they gave us this on the left-hand side, and it should be equal to this on the right-hand side. So I'm going to take the left-hand side and say it's equal to, and rewrite it first. Okay, so we're trying to get it to look like this, 1 over cos x. So something I already noticed is it's a cos x, not 2x. So I'm definitely going to change that. So with the sine 2x, you know that you can use double angles, okay? So the double angle identity for this would be 2 sine x cos x. Okay, so that is gone now. And then over, 2 cos squared x. So here the 2's would cancel and the 1 cos x would cancel. And then we have plus, and then over here we have sine x. And then, we can actually just simplify that. That's cofunctions. Then we have a tan x. With the tan x, you can change it to sine x over cos x. And then we'll just see what it cancels with, since we just have a cos x left here. Okay, so we have 1, then plus, you have cos 90 degrees minus x. The identity that goes with this, okay, with cofunctions is, this is equal to sine x. So we're just going to say this is plus sine x, okay, and this is what we have. And now what cancels is these two are gone, a cos x here, and that cos x is gone. So this is equal to, we have sine x over cos x. Interesting. So that is, tan x, but okay. Okay, and then plus, now with this, what I'm going to do is, I'm going to take this sine x and divide it by this sine x over cos x, just so that you see what happens there. Okay, so this is a numerator here, and then that is the denominator. We're saying this is sine x divided by sine x over cos x. Okay, because these two are multiplying, I can actually do that. I can divide this with this first, and then still put it, wherever it should be at the end of the day. And then we can use step in times. So you're going to change the division to a multiplication, and you're going to swap the numerator and the denominator. Okay, so now when multiplying, do you see that across? Okay, because this actually has a natural denominator of 1. So across, we have sine x and sine x that will cancel since we're multiplying. And then all that will be left is the cos x. Okay, so I said this divided by this, and all that was left was cos x. So that would go to the numerator. That's what we would have there. Okay, so what we have left here is we have cos x over, now remember all of that is gone, it's just cos x, and then the denominator, this is left, the 1 plus sine x. So we just have cos x over 1 plus sine x. Okay, and now we are adding these two fractions. So to add fractions, you need to ensure that their denominators are the same. Right now, this is cos x, this is 1 plus sine x. So the only way to make them the same is if you multiply this one, its numerator and denominator, by 1 plus sine x. And this one, its numerator and denominator, simply multiply it by cos x. Okay, so cos x. And then that would really just sort that out. So your denominator is going to be cos x times 1 plus sine x. I won't FOIL out yet because I don't know if that's going to be useful or not. We'll see. Then when we multiply, this is one term times two terms. So the sine x multiplies to the 1 first and becomes sine x. And then the sine x multiplies to the sine x to become positive sine squared x. Then we have plus, okay, there. And then cos x multiplies to cos x to become positive cos squared x. And we already have our denominator. Okay, do you see how we have an identity here? Okay, we have sine squared x plus cos squared x, which gives us 1. And yeah, so that's actually what cancels with this. So that 1, I'm going to put it here. Then I'm going to say we have a positive sine x. And then this goes all over cos x times 1 plus sine x. And now do you see how this and this would cancel? They can perfectly cancel since these two are multiplying. So we have one term in the numerator. Okay, we can see this as one term. And then one term in the denominator because of the bracket. So this cancels with that as a term. And then all that is left is in the numerator, we still have a placeholder of 1, okay? Because you're saying this divided by this. You're really just saying, so we're just saying because they are common, we said 1 plus sine x, really just divided by 1 plus sine x, and then that gives you 1. So the 1 is in the numerator. And then this, 1 plus sine x divided by 1 plus sine x also gives you 1. That's in the denominator. But you know 1 times cos x still gives you cos x. So at the end of the day, we just have 1 over cos x. And that's exactly what they said it should be. That is the right-hand side. And we can finally tell them, yes, it is equal to the right-hand side. Okay, so the left-hand side at the end of the day is equal to the right-hand side. Moving on to the next question. Okay, next question, 5.3 says, show without using a calculator that sine 260 degrees is equal to all of this. Okay, can we get sine 260 degrees to end up being equal to all of that? Okay, let's try. So with this, we're using sine here, but you see how it ends up being equal to something with cos. So what do you think they used to change sine to cos? They must have used cofunctions. So we're probably going to use cofunctions, but I also noticed that this 260 degrees is quite big. So let's reduce that. So where would 260 degrees lie? 0 degrees, 90 degrees, 180 degrees, 270 degrees. So 260 degrees is somewhere here. Okay, and so because it is in the third quadrant, you're going to use that reduction, which is 180 degrees plus theta. So 180 degrees plus what gives you 260? Just say 260 minus 180 quickly. Okay, so that's 80 degrees. So I know that this can be sine. Okay, let's just work through it one step by step. Okay, so we'll just say 180 degrees plus the 80 degrees. That's what gives you the 260 degrees, right? And so if you reduce this, because this is actually in 10th quadrant, where sine is negative, it will become negative sine 80 degrees. Okay, this is what we have so far. Negative sine 80 degrees. How do we get this to look like this? So I can still say there's a cos. How did they change it to cos? Using cofunctions. So let's look at our cofunctions. Okay, so these are our cofunctions, and you can see that with 80 degrees, here's how we look at them. So with cofunctions, you're going to have angles that are greater than 90 degrees and angles that are less than 90 degrees. The ones that are less than 90 degrees are these ones, the 90 degrees minus theta. The ones greater would be the 90 degrees plus theta. So 80 degrees is an angle less than 90 degrees, and so we can express this as negative sine, and we can say 90 degrees minus what gives us 80 degrees. That is 90 degrees minus 10 degrees. And now we can finally use cofunctions on this. So we know that sine 90 degrees minus theta, okay, that's cos theta. So sine 90 degrees minus 10 degrees, we will still have the negative, and then this becomes cos 10 degrees. Okay, so that's what we have there. Okay, so the thing is still, how did they get this? So we have the negative, great. We've got the cos, but then this is 10 degrees and this is 20 degrees. How did they do that? Well, this is something that you will notice from trig diagrams, but it's one of those trig diagrams that is, we'll call them unusual, okay? They're not that unusual anymore. They've been using them for a while. So you know the trig diagrams where we have something like sine of 23 degrees is equal to P, right? So with these questions, one of the questions that they like to ask is, let's just take an angle like 24 degrees, okay? They would maybe ask you for something like, find the value of cos 12 degrees. So you know how in this question, in this type of diagram question, you have to relate everything that they give you, all the angles they give you, you have to see how do they relate to 24 degrees, okay? For example, let's say they ask you for something like this, you have to draw a diagram, and then they say question 1 is that you need to find the value of cos 156 degrees. And you look at this and say, okay, it gave me 156 degrees. How does this relate to 24 degrees? So you can start with the fact that, hey, this is an obtuse angle. Let me try to reduce it using the reduction diagram. And so 156 degrees is an angle greater than 90, but less than 180 degrees. So it's here. And so you'll use this quadrant's reduction. This is sine's quadrant, and its reduction is 180 degrees minus theta. So you would just say, okay, so this is cos 180 degrees minus, you don't have to write that part, but it's going to be 180 degrees minus what gives me 156 degrees. And then you'd find that. So 156, okay, or 180 minus 156, that gives you 24 degrees. And now do you see where the 24 degrees comes in? Okay, so because of that, that would reduce to, remember, this is cos, but that is in sine's quadrant. This reduction is in sine's quadrant, so it reduces to negative cos 24 degrees. And then you'd be able to find this because your diagram would have 24 degrees measured in it. Okay, you'd measure 24 degrees, and then you'd be able to find what cos of this is, since you have, sine of this is equal to p, and all the other sides, okay, the opposite, the hypotenuse, and the adjacent side. With this question, they like asking this type of question. It's a very famous question. You'd always look at the angle and ask yourself, what does this have to do with 24 degrees? Well, 24 degrees, okay, you know that 12 degrees is half of 24 degrees. And so, because you have half of it, it's like, how do you now get to the answer? It's by using the fact that this is half of this, meaning this angle, 24 degrees, is double of this. So we would be using double angles. Here's the thing with your double angle identities, right? Let me put that down so that you can just go ahead and look at them. Remember, they are in your formula sheet. Okay, so these are our double angle formulas. So with these, do you see how we know that, okay, what they use is they have 20 degrees, but we have 10 degrees. So they clearly used double angles to form this. Now, because in what they have, do you see how they have cos? They've got 2 and there's a 1, okay? Look for a formula here that has like 2, that's cos, and has 1. That would be this one. So here's how we can do this. We're going to take this, right? And I'm actually just looking for the value of cos 10 degrees. That's all I'm trying to look for. So I'm going to use this. I'm going to tell them that I know that, well, this part you don't have to write, but I'm just going to put it here so it makes sense. So cos 2a is equal to 2, and then we have cos squared a minus 1, right? But over here, our angle is 10 degrees, okay? So we're trying to find cos 10 degrees. Do you see that where we get the cos, okay, and not the cos 2a, that would be here. So this is cos squared a, but there's a cos a here. So that's a cos a, and then it was squared. So here with this, what I'm going to do is I'm going to call this cos 2, and I'm really just calling the a 10 degrees. So wherever I see a, I'm going to replace it with 10 degrees. So this is cos 2, and then times 10 degrees. And then it's equal to 2 cos squared, and then that's 10 degrees, then minus 1. Okay, the biggest hint with this is if what you're looking for is half of what they gave you, then you can see this is double angles. Okay, because this is 10 degrees and then 20 degrees is double of that. So definitely they used the double angle formulas for that, one of them. Okay, so this is what we have. So cos 2 times 10 degrees, that's what we get our cos 20 degrees. And then this is equal to, and it's still equal to all of this. Remember, all we are trying to do is find the value of cos 10 degrees, so we can put it back in there. It's going to naturally include cos 20 degrees. So we need to isolate the cos 10 degrees, and that's really all we're doing now. Okay, so how do we isolate that? Well, we can start with taking this negative 1 over because we have two terms here. The first problem is the negative 1. It needs to go over. So we're going to have cos 20 degrees and then plus 1 is equal to, now we have 2 cos squared 10 degrees. Then we need to get rid of the 2. So to get rid of the 2, you can simply just divide both hand sides of the equation by 2, And finally, we have here, this is just going to be I'll just put this on the side just to make it easier. So I'm going to call this cos, and I have squared 10 degrees is equal to, and all I have here is cos 20 degrees plus 1 over 2, okay? And finally, to get the value of cos 10 degrees, you see that you just have to square root both hand sides of this equation. Okay, now this is the value of cos 10 degrees, okay? 10 degrees, if you had to measure that, you see that 10 degrees would simply be in the first quadrant, okay? So even if you had to consider positive and negative solution, it's definitely going to be positive because cos 10 degrees, okay, it's cos of an angle. You're going to really just say, take the adjacent side, let me use theta, the adjacent side over the hypotenuse. The adjacent side is a positive x value. The hypotenuse is also a positive because it's a radius. Okay, so it's always going to give you a positive. So you don't have to consider the negative there. And so therefore we'll just say cos 10 degrees is equal to the square root of cos 20 degrees plus 1 over 2. Now we're not done. We were just trying to find the value of cos 10 degrees. Okay, so here I can just say, but I know about this, okay, using the double angle identity. And so now I'm going to put it back into this equation. So I know that what we had was negative cos 10 degrees. So this means that negative cos 10 degrees is actually equal to, you're just going to say negative and then whatever cos 10 degrees was, which is all of this. Okay, so I just put that in and this is our answer. Okay, so at the end of the day, cos 260 degrees really is equal to negative and then the square root of cos 20 degrees plus 1 over 2, just like we have. So you can finally conclude that you know that sine 260 degrees is equal to that. Okay, so we have proven that. That's what they asked us to prove, and we proved that. Remember, these don't have to be there. I'm just leaving these as explanations because I'm also going to just put this on my website so you can also just access the workings of this. Okay, so that is it for that question, and that is it for question 5. We are on question 6, and question 6.1 says, given, and we have all of this, and they want us to, without using a calculator, simplify the above expression to a single trigonometric ratio. So it should just be a single trig ratio. So, it can be something like sine 20 degrees, something like that, basically. That's a trig ratio that we have. Okay, so let me rewrite this first. Okay, so to simplify this, you can see the numbers they're using. We need to reduce these numbers. Okay, so let's just see. 330 degrees, that, when using the reduction diagram, that is an angle greater than 270 degrees, but less than 360 degrees. So it lies in the fourth quadrant, which is where cos is positive and has this reduction. So if we were reducing this, you say 360 degrees minus what gives you 330 degrees? 360 degrees minus 30 degrees. So that would be, 360 degrees minus 30 degrees, because I'm not going to leave these here. I'm just showing you so that it makes sense. Say 360 degrees minus theta, you say 360 degrees minus 30 degrees. Then reduce it using this. Okay, so this would reduce to positive cos of whatever your angle was, which is 30 degrees. Okay, so this becomes positive cos 30 degrees, a special angle. Okay, times, and then we have cos 365 degrees. Do you notice anything weird about that angle? That angle is greater than 360 degrees. Okay, so all you need to do, it's really just like you measured here, you measured 360 degrees, and then you just went 5 degrees extra. So all we're just going to do to find out the value of this, so it's easy to work with, is because we went like that and just ahead of 360 degrees, we're just going to go back, okay? Because at the end of the day, the angle is just this. You just need to go back by 360 degrees. So when the angle is greater than 360 degrees, you simply subtract by 360 degrees. So we can understand the value of that angle. So 365 minus 360 degrees is just 5 degrees. So we have cos 5 degrees over there. Then plus, and then you have 175 degrees. 175 degrees is an angle greater than 90 degrees, but less than 180 degrees. So it lies in sine quadrant and it has this reduction. Okay, so it means that what we would have is sine, and we're saying 180 degrees minus what gives you 175 degrees. That would be minus 5 degrees. And then when you reduce this, you can see it's going to reduce to positive sine 5 degrees, since it is a reduction in sine quadrant where sine is positive. So positive 5 degrees. Then multiply by, and then we have 210 degrees. Okay, so 210 degrees is an angle greater than 180 degrees, but less than 270 degrees. So we will use this reduction, 180 degrees plus theta. And so we have times, and we have sine, and this is 180 degrees plus what gives you 210 degrees. That is plus 30 degrees. So when reducing this, remember it's sine, but this is tan's quadrant. Tan is positive here. So this would reduce to negative sine of 30 degrees. So this is negative, okay, negative sine 30 degrees. And now all we are doing is simplifying. And you can already see from the structure, they're clearly using compound angles. Okay, so cos, sine, sine. Okay, so this is equal to, none of these would change. They just stay exactly the same. Okay, and then we would have, you see, sine 5 degrees times negative sine 30 degrees just becomes negative sine 5 degrees sine 30 degrees. Okay, so that's what we have. And now finally we can just simplify this. Okay, so you can see that they have clearly used this rule, cos A, cos B. So that's now your A, that's your B. Then you have minus sine A, sine B. Okay, so in this same way, the way this simplifies to cos A, and then the sign changes to plus B, it's the same way all of that would change to cos, and now A is 30 degrees, and then plus that is 5 degrees the B. Okay, so that's actually what it simplifies to. And then just simplify it further. So this is cos, and this is 35 degrees. That's the single trig ratio they were asking for. Cos 35 degrees is our answer. Moving on to the next question. The next question, 6.1.2, says, hence, determine sine 70 degrees in terms of P if, and okay, yeah, looks familiar again, if all of this is actually equal to P. Yeah, I was waiting for that trig diagram. I was wondering, there's no diagram today, but then, yeah, there actually is one. So, you know how all of this simplified to cos 35 degrees, like we saw, okay? So we're just going to replace that with cos 35 degrees. So this is now cos 35 degrees, which is actually equal to P. And we need to determine sine 70 degrees in terms of P. Okay, so this is a trig diagram situation like you saw when I was explaining question 5. So what we do here is we're simply just going to draw a diagram. So if you measure 35 degrees, okay, using those quadrants, you will see that 35 degrees is an angle that would lie in the first quadrant. So our terminal arm can be here, and we can just say this is 35 degrees. Okay, and just say 35 degrees, and there we go. Then you will draw a line down to your x-axis perpendicular to that x-axis. So they said cos 35 degrees equals P. That's what we have. So cos 35 degrees, we're going to say cos, okay, using SOHCAHTOA. Cos, we will take the adjacent side over the hypotenuse side. So this is P. Okay, it's adjacent over hypotenuse, meaning we have a denominator here. Since this is just P, the natural denominator is 1. And so this means that this is the adjacent side and the 1 is the hypotenuse. Okay, so here's 35 degrees. This is opposite. This is adjacent. So this is your P over here, and then your hypotenuse is 1. And so all we need to find is the opposite side. And of course, when you look at that value, that lines to a y value. So I'm simply just going to call that y, and then we have to find that. Okay, so to find that y value, you use Pythagoras. So we're trying to find a shorter side. The hypotenuse is the longer side. So we have y squared is equal to the hypotenuse squared minus the other shorter side squared. And then you need to find y. So you'd square root both hand sides. Normally, we take the positive and negative solution, which is still correct. But you can see that here the y value is clearly going to be a positive value. It's on the positive part of the y-axis. Okay, so we're just going to say y is equal to the square root of 1 minus p squared. Okay, so that is what we have there. Square root 1 minus p squared. And now we can find what they want us to find. They want us to find the value of sine 70 degrees in terms of p. Okay, so this is sine 70 degrees. Again, with question 5, remember when I said once they give you an angle, whatever questions they ask you, you're always going to look at that angle and ask yourself, what does this angle have to do with this angle I already have? Because that is the only way you can relate it to your diagram. So 70 degrees and 35 degrees, what do they have to do with each other? Well, 70 degrees is double of 35 degrees. So we can clearly see they're using double angles here. So look at how we can rewrite this. We can call this sine, and you can say 70 degrees is double of 35 degrees. Okay, so this is what we have. And now we can't just find this like this. You're going to have to use one of the double angle formulas. With sine, okay, sine 2a, it's very simple. It's only this one. So it's 2 sine a, but our a here is our 35 degrees, and then cos a, 35 degrees. So we're saying 2 times what is sine 35 degrees. So we're looking at our diagram. How do we find sine? Okay, using SOHCAHTOA, sine is the opposite side over the hypotenuse. So let's go. Take opposite over hypotenuse. It's just going to be this over 1, which you can see would just simplify to that square root 1 minus p squared. Okay, because over 1 stays the same. Then multiply by cos 35 degrees, which we already have. Okay, cos 35 degrees is p. So just rewrite it as p. And then just simplify this. So you have a root, which will come after. So just say 2 times the p, which gives you 2p. And then square root 1 minus p squared. And that is our answer. Okay, so moving on to the next question. Okay, question 6.2 says, it is given that, and I just had to emphasize on that because when it was scanned, yeah, that smudged it out. Okay, so 6.2 says, it is given that 2 to the power of 3 sine squared x and then over 4 times 2 to the power of sine x is equal to 1. Okay, it may look intimidating, but it's really simple because you just have 2, an exponent, 4, which can be written as 2 an exponent, and then you also have a 2 an exponent, okay? So determine the general solution for x if sine x is less than 0. I kind of like it when they do that because our work is lighter since they already put in a restriction. So there's one equation that we're going to just leave, and we're not even going to try to find the general solution of that. And then the one where sine gives us a negative, okay, less than 0, that's what we will go with. Okay, so we're just trying to find the general solution. Let's go. I'm going to rewrite that. Okay, so this is what we have, and we need to find the general solution of this. Okay, so remember how we just have 2 to the power of something, and 4, and then 2. We can start with the 4s. Okay, this is just an exponential equation at the end of the day. So we're just going to simplify that denominator. We have 2 to the power of 3 sine squared x all over, and then 4 can be written as 2 squared. Okay, multiplied by 2 to the power of sine x is equal to 1. Then rewrite the numerator. Okay, and then we have, now you see when the bases are the same and you're multiplying, then you would add the exponents. So what we're going to do is say 2 to the power of, I would like to put that as sine x plus 2. Okay, you can say 2 plus sine x, but I want it like that. So it's equal to 1. And then now we can finally work with dividing. So now the bases are the same and we're dividing. So what you do to the exponents, you would subtract the exponents. So you leave the base the same. And in the numerator, we have 3 sine squared x minus, and we're subtracting by something that has more than one term. So use brackets. So we'll say sine x, or you can just say minus sine x minus 2. That's fine. Okay. And then is equal to 1. Okay, I can already see at this point I have to, because it's an exponential equation, I need to make the basis the same. So I might as well just do that at this point. I'll say 2 to the power of 3 sine squared x minus sine x. I said, sorry about that. This should be a plus 2. Okay, then when it multiplies in, it becomes minus. So minus 2. Okay, that was close. Okay, and then here, 1. So at this point, what I'm trying to do is I'm trying to solve for this exponential equation where we have a base of 2 here and then we have a base of 1. To solve for an exponential equation, you have to ensure that the bases are the same. Okay, so you can make the exponents equal. So how can we rewrite 1 as a base of 2? By writing it as 2 to the power of 0. Okay, so there we are. And now the exponents can be made equal. So we have 3 sine squared x minus sine x minus 2 is equal to 0. Okay, this is a very creative way of writing that. So all we have to do is solve for this. Okay, we're going to have to factorize clearly, and then we'll see. Okay, so I know this can look intimidating, but what you can do is, if it is, you can just say, let sine x be equal to k. Okay, but just do this on the side. You don't have to tell them this. So we'll have 3, that's k squared, and then minus k, and then minus 2. Do you see how this is a trinomial, and you have to factorize it? Okay, then you can factorize the trinomial. I'm just going to factorize it as it is, so that you guys also still get used to working with it as sine x, because sine x is just serving as a variable here. So I'm going to get the factors of the first term, which is 3 sine squared x. So that is 3 sine x multiplied by sine x. That's what gives you 3 sine squared x. And then the factors of the last term, which would be 2 and 1. Okay, but it just depends on how you put them. Now, when you cross multiply them, they should give you the middle term, negative sine x. So let's think about that. First of all, this is negative, meaning one of these should be negative, one should be positive. So what we can do is, let's think about this. We can cross multiply first before we decide. So 3 sine x times 1 is 3 sine x. And then sine x times 2 is 2 sine x. Which one should be negative so that you can get a negative sine x in the middle? You should make this one negative, the one with a bigger variable. Okay, so negative 3 sine x plus 2 sine x gives you negative 1 or negative sine x. And that's how we'll get that. So how did we get the 3 sine x? We got that by saying 3 sine x times 1. So that is what gets the negative. The 1 takes the negative and the 2 takes the positive. Okay, so like that. And so we know our factors are 3 sine x plus 2. And then sine x minus 1 is equal to 0. And here we are. Okay, so this is just a factorized version of that. And so you're saying something multiplied by another thing gives you 0. It's either that the first, so 3 sine x plus 2 is equal to 0, or the second is equal to 0. So sine x minus 1 is equal to 0. And so here's what we get here. We get 3 sine x is equal to, we'll transpose the 2, becomes negative. Then divide both hand sides by 3, and so sine x is simply equal to negative 2 over 3. Okay, and then here, sine x would just be equal to 1. And now we can stop and go back to the restriction. Remember how they said we need to solve, okay, specifically where sine x is less than 0. In other words, where sine is negative, okay, where sine x is negative, gives us a negative value. Do you see here that sine x gives you a negative? That's what we're going to go with. Okay, so we're not going to take this. I'll just say not applicable because you guys said sine x is less than 0. Okay, I'll leave that. And now we just go with this. And we just need to find the general solution for this equation. Okay, it's not specific solutions, it's just general solution. So we need to first find the reference angle. I'll just use the table method here. So reference angle equals, and you're going to take your calculator and you're going to transpose sine. Okay, so shift sine, and you're saying 2 over 3. So I'm not going to take the negative of it since I'm using the table method, the one with your reductions. Okay, so that's going to be 2 over 3, and then that's the angle I get. At this point, I'm going to round off. And it's not a problem because we're trying to solve for x, not 2x. So we don't have to still divide at the end of the day. Okay, so I'll say 41.81 degrees. Okay, so we have that down. And now this is going to be equal to. So you see how sine, okay, is negative. Sine x is equal to a negative value. So let's look at the quadrants we're going to consider here. Where is sign negative? So sign is negative in the third and the fourth quadrant. This is in tan and cos's quadrant, and we know that the reduction here is 180 degrees plus theta. Here it's 360 degrees minus theta. So to solve for x, we'll now say x is equal to, and use these reductions. So this is 180 degrees plus our reference angle, which is 41.81 degrees. Remember, this is general solution. You're finding the solution, so the infinite solution on the sine graph, where the sine graph has a y value of negative 2 over 3. So you have your sine graph, and you're just saying, where do you have a y value of negative 2 over 3? Okay, so this graph just continues forever. It's going to go like that again and like that. So you're just trying to find out all the places where it will forever have that y value. Okay, so because of that, you must say plus k of, and remember that the sine graph repeats itself every 360 degrees. 360 degrees later, you have another sine graph. So that answer of negative 2 over 3 will appear again. So let's say it was here, okay? Between 0 to 360 degrees, you have an answer here and here. Then, with the next cycle of the sine graph, again, you're going to have answers here and here. And it'll just continue infinitely, even at the negative side of this. So we say k 360 degrees, or, and then x is equal to, now the second solution would be, okay, so we'll say 360 degrees minus, and our angle is 41.81 degrees, again plus k 360 degrees. Then you can tell them where k is an element of integer values. That's what we're going to use. Okay, and now we can get the final answers. So x is equal to, and I'll just find that. So what is 180 plus 41.81 degrees? That gives us 221.81 degrees. And you say plus k 360 degrees, or, and then here x is equal to, you must just say 360 degrees minus that. So we'll just say 360 minus, and then that gives us 318.19 degrees plus k 360 degrees. You don't really have to write this again, but I'm just going to say again where k is an element of integers. And that is our answer. Okay, so that was the last question. Okay, and that concludes it for question 6. Moving on to question 7. We are now on question 7, and question 7 says, in the diagram, we have f of x is equal to 2 sine and then x minus 45 degrees. Okay, so this is a sine graph, okay, that has been shifted 45 degrees, but remember it says minus. When it says minus, when we are affecting the x, okay, it means it's shifted to the right. Okay, if it says plus, it was shifted to the left. So it is drawn for the interval where x is an element of negative 180 degrees to 180 degrees. And yeah, it's also good to note that these actual values, negative 180 degrees and 180 degrees, they are included. Okay, so there's an actual point on this graph with an x value of negative 180 degrees and 180 degrees. Okay, so 7.1 says, write down the amplitude of f. What is the amplitude of f? Well, you can look at the amplitude by looking at the equation of that graph, which is 2 sine x minus 45 degrees. So the amplitude will appear in front of sine, okay? So you're always going to take the absolute value of whatever this is, okay? The coefficient of that sine. So in this case, it's just 2. Even if it was negative 2, the amplitude would still be 2 because you need to take the absolute value of that. The absolute value of negative 2 is just 2, okay? Okay, so that is simple. Our amplitude there is simply 2. Moving on to the next question. 7.2 says, determine the values of x in the interval, okay, so in the same interval, for which, but they say f prime of x is greater than or equal to 0. So what does f prime of x mean? You know, in calculus, when we find f prime of x, we're finding the derivative, right? But the derivative means gradient. So you're trying to find the gradient of a function. And so they're saying tell us where f prime of x is greater than or equal to 0. Let's speak about where f prime of x is greater than 0. This is referring to the gradient. Where is the gradient greater than 0? In other words, positive. The gradient is positive, okay, wherever the graph is increasing. So if you have a straight line and it looks like this, you always read graphs going from the left to the right. So this graph is increasing, okay? And then if you have a straight line like that, then again, read it from left to right. This graph is decreasing. So when you find the equations of these lines, you'd expect this one to have a positive gradient, this one to have a negative gradient, okay? So we're going to look in our graph and look for all the places where the graph of f is increasing, okay? But then they also say equal to 0. So you're looking for where it is increasing, but then where the gradient is equal to 0, okay? Works like this. You can think about a parabola, for example. Let's say we have a parabola. The parabola does two things, okay? It has two types of gradients you're going to see. There's a turning point here, and then if you read it from left to right, here the graph is decreasing. And then over here, it is increasing. Then at this point, okay, this is where the gradient is the graph is neither increasing nor decreasing. At this point, this is where the gradient is equal to 0. So what they want us to find is the places where the graph is increasing, but you must also include any turning points that you see. Okay, so where the gradient is equal to 0, just know that is at the turning point. Okay, so let's look at our graph and see where is this graph increasing. Read it from left to right. What is it doing here? It is decreasing. Then what happens? You have a turning point. Okay, so there at that minimum, not maximum, minimum. Okay, and then what is it doing here? It is increasing. That's what we're looking for. Then there's a turning point there. So what we're just looking for is this area over here, and we must also, of course, include the turning point. Okay, so we need to find out exactly what this is and what that is. Now, you just need to remember what this graph was. This, okay, it was a normal sine graph, or one with an amplitude of 2, right? But then this graph, remember, it has minus 45 degrees, meaning this graph was shifted 45 degrees to the right, okay? So with this graph, we would have to move it back to where it originally was. Since it was shifted 45 degrees to the right, shift it back 45 degrees to the left. If you did that, look at what you would have. So you see how if you have a normal sine graph, it's naturally supposed to start at 0 here like this, okay? It's supposed to look like that. But then it was here instead. So that means it was supposed to look like this. Then it was shifted 45 degrees to the right to look like that. So all I'm trying to figure out is what exactly is this angle over here? You're just going to take what its previous value was, okay? This is the maximum value, okay? The previous maximum value should occur at 90 degrees. But then the graph was shifted 45 degrees to the right. So just say 90 degrees plus 45 degrees. And you get that, okay? 90 degrees plus 45 degrees, that is 135 degrees. So 135 degrees, that's what we have there. And then we will do the same thing to find this angle here, okay? So looking at the original graph, okay, the one with the thin red line, this graph was shifted 45 degrees to the right. So before, its minimum value used to be at negative 90 degrees. Then they took it and then they shifted it 45 degrees to the right. And so it's now at negative 45 degrees. And there we have everything that we need now. Okay, so I'll just put that down. Okay, so I don't really need any of those. And there we go. Okay, so I can erase that. So we know these, and now the places where the graph is increasing is simply from all of these places. Look at all these. So take the highlighted part, line it to the x-axis so you can understand what the x values are. Look at all these x values. These are x values that are going from negative 45 degrees all the way to 135 degrees. That's all the x values that we have here. And so you can write it like this. I'll go ahead and write it in interval notation because I feel like that's going to make more sense here. So x is an element of, it goes from exactly from this point, negative 45 degrees all the way to positive 135 degrees. Okay, notice the brackets I use here. I use square brackets because these points are actually included. They specifically said they want where f prime of x is greater than 0, but also equal to 0. Okay, at the turning points, that's where f prime of x, or your gradient, is equal to 0. Okay, so that would be our answer. You can write it like that. We can also write it in set builder notation, which will look like this. You're simply saying x is going from negative 45 degrees to 135 degrees. So greater than or equal to negative 45 degrees, but less than or equal to 135 degrees. And that is fine. Okay, that is our answer. Moving on to the next question. Okay, the next question, 7.3, says, on the same set of axes provided in the answer book, draw the graph of g of x is equal to negative tan x. So there's a new graph, g, okay, negative tan x, for the same interval. Okay, it's just the tan graph, just with negative in front of it. So think about what the tan graph looks like. With the tan graph, first put down those important things that you need. Your asymptotes. The tan graph, okay, it's a graph that completes one cycle in 180 degrees. So this is what the tan graph looks like normally. Okay, so you have from 0 to 180 degrees, and the graph would look like this. There is an asymptote at 90 degrees. And remember, this graph is going to repeat itself every 180 degrees. This is the tan graph. Okay, and then it's going to do this. With the tan graph, rather counting 45 degrees is going to be helpful because important things happen every 45 degrees. So for example, at 45 degrees, the tan graph reaches a y value of 1. And then after 90 degrees, 135 degrees, the tan graph reaches a y value of negative 1. Okay, so you'll be able to put that down. You'll be like, okay, that's 1 there. This is negative 1. And then the tan graph just looks like this. It goes from 0 and it hits that one, shoots up. Okay, never touches the asymptote. And then it comes from being really close to the asymptote. Okay, I think I should just put my negative 1 like here. Make more sense. Okay, comes from being really close to the asymptote, and then it goes like that. And then it's just going to finally get to 180 degrees and it's shooting down there. Okay, not really the best looking tan graph. I think I should just do this. There we go. Okay, so that's just the rough sketch of what it looks like. So first thing, put down your asymptotes. We have an asymptote at 90 degrees. This is not going to change just because you put a minus in front of this. The minus will not do anything to that asymptote, okay? The only thing that would affect it is if you now actually took that graph and shifted it, like to the right or to the left. Yeah, then those asymptotes would be affected since they are vertical lines, okay? If it's shifted, then, it could be over there, for example. Okay, so there is our first asymptote. And then remember that these asymptotes, they repeat, just like the graph, every 180 degrees. So if we had more intervals here, then we could have had another asymptote at 270 degrees, but it cuts off at 180 degrees, so we're done there. Then you're also going to have to look backwards. So this graph is also going to have an asymptote 180 degrees before this. So 90 degrees, if you go 180 degrees behind, or backwards, you're going to get to negative 90 degrees. So there, another asymptote is over there. Okay, so done with the asymptotes, I'll just label them. This is where x is equal to 90 degrees, okay? So it's a vertical line. Its equation always starts with x is equal to. You can remember it by simply saying it is a line that only cuts the x-axis, okay? Doesn't cut the y-axis. So you just say x is equal to whatever value it cuts the x-axis at, okay? Same thing here, like that. That's how we got that. And then x is equal to negative 90 degrees. And there we are. Okay, and then see from the way our tan graph looks from 0 to 180 degrees, do you see how it had a y value of 1 before, right? This is the graph of y equals tan x. But now you put a negative in front of it. They put a negative here. So it's not going to have that 1 anymore here, okay, at 45 degrees. It's going to be that 1 times the negative 1, because you're really just saying negative tan 45 degrees. If tan 45 degrees gave you 1 before, this is now going to give you negative 1, okay? So we're just going to put that down. So we know here at 45 degrees, which is this, and I should really just point it out. This is 45 degrees because that graph was shifted 45 degrees to the right. It used to be at 0, it moved, and now it's at 45 degrees. Okay, and then this, of course, would be negative, so negative 90 degrees, and then 45 degrees behind, it's negative 135 degrees. Okay, so our tan graph at 45 degrees now has a y value of negative 1. So here, negative 1 and 45 degrees is what we have. Then at 135 degrees, where it should have had a y value of negative 1, what's going to happen? It's going to get multiplied by negative 1 to become positive 1. And so now we have 135 degrees and positive 1. So like that, here's a positive 1 and 135 degrees. Okay, so now let's just draw what the first cycle of the tan graph looks like. You're going to go from 0 degrees and then connect to the next point. But we know ours is going to be negative. So with the way theirs looked, ours is going to look like this. So it's going to get negative 1. This is going to have 1. So it's going to do this. And it's going to do that. It's going to look like that. Okay, like the red one. So we will connect it from 0 degrees. You hit that 1, that negative 1, and then you move closer and closer to the asymptote, never touching it. Then here, I will just go from 180 degrees, and I'll hit there, and move closer and closer to the asymptote, never touching it, okay? Here, at 180 degrees, has a y value of 0. 0 degrees, it has a y value of 0. And now you just have to do what you did here, okay? So you see how you had from 180 degrees, and you went up close to the asymptote. We'll do the same thing here. From 0 degrees, you're going to go closer to that asymptote like this. So at negative 45 degrees, this is where you have a y value of 1. Okay, these answers, they just repeat themselves every 180 degrees. If you go from 135 degrees and you go 180 degrees backwards, you're going to get to negative 45 degrees. Okay, so once you know what this one looks like, you know what the other one looks like. Okay, so there we have 1. And so the graph is going to do this, move closer to the asymptote, never touching it. And then same thing here. So we have this. You see how that had a y value of negative 1. This will also have a y value of negative 1 at negative 135 degrees. So here, and then you just put that down, say negative 1. Okay, so there. And then at negative 180 degrees has a y value of 0. And your graph is just going to do this, exactly what the other one is doing. Okay, move closer and closer to the asymptote, never touching it. And that is our graph of G. Okay, everything is down. Yeah, that is it. Moving on to the next question. The next question says write down the value of, and they want us to do this. Okay, so G of negative 45 degrees minus F of negative 45 degrees. So what is the y value at G and what is the y value of the graph at F? So let's go to negative 45 degrees, which is over here. And then do you see that the y value of the graph of G, okay, the graph of G has a y value of 1 here. And then the graph of F has a y value of minus 2, because that's a minimum value there. So they're just saying 1 minus negative 2. Okay, so we're just going to say, we know that the y value there is, I'll just put it down first. Y value there is 1 minus, and then negative 2, which is equal to 3. Okay, so there, that's the value of it. It's 3. Moving on to the next question. Question 7.5 says, how many solutions does the equation g of x minus f of x equals 0 have in the interval? And it's that same interval. It is for 1 mark, okay? So they just want to see how many solutions does this have. Do you notice that this just has a minus f of x? Why don't we just take that over so we can better understand this equation as g of x is equal to f of x, okay, positive f of x. They're just saying count the number of solutions you have for this equation. Okay, so when two graphs are equal, if we're trying to see where f of x is equal to g of x or g of x equals f of x, you're just trying to see all the places where they intersect. Because if they intersect at a point, that means they have the exact same x value and the exact same y value. Okay, so this is where their y values are exactly the same. So let's see, where do these graphs intersect? So all through here, I see, there you go, they touch here. Both of them intersect here. And they intersect here. Okay, any other points of intersection? Doesn't seem like we have any other. So those are the solutions we would have. 2 solutions. Okay, you can't say this is a solution because the graph of G does not have a y value here. There's an asymptote. Okay, this is undefined. So it's just those 2 places. We can just tell them two solutions. Okay, moving on to the next question. Okay, question 7.6 says, graph H is obtained where G is translated 45 degrees to the right. We need to write down, that is the equations. Sorry about that. So the equations of the asymptotes of H in the interval where X is an element of, and this is what we have, okay? Again, the same thing. So this time the graph of G is being shifted, okay? 45 degrees to the right. So you see, it forms this new graph, H of X. And here's what we're going to do. I don't actually have to write the equation of it. I find that unnecessary. It's not necessary because it's not going to help you. Focus on what they asked for. They want the equations of the asymptotes of H, this new graph. So let's go ahead and shift G 45 degrees to the right and see what will its asymptotes now be. Okay, so currently the blue graph G, look at its asymptotes. It's at negative 90 degrees and positive 90 degrees. These are the current equations. When it gets shifted 45 degrees to the right, what happens? This line is literally going to move 45 degrees to the right and it's going to land here. Okay, so at negative 45 degrees, and then the other one is going to land here at 135 degrees. You literally pick up this line. Okay, I could just draw a line there, and then you pick it up and you move it 45 degrees to the right. Okay, so pick it up, move it 45 degrees to the right. And there we go. And the other one as well. Okay, so the new equations, it used to be that. Now it's X is equal to negative 45 degrees and X is equal to 135 degrees. And that would be our answer. Okay, so we'll just tell them new equations. X is equal to negative 45 degrees and X is equal to 135 degrees. And that is our answer. And that is it for this question. Okay, question 7. And moving on to the final section of the trigonometry part of this paper. Okay, we are on the final section of the trigonometry part of this paper, and we have question 8.1. So question 8.1 says, in the diagram, we have triangle RTP is given with RT being equal to P and RP being equal to T. They want us to prove that sine angle T over T is equal to sine angle P over P. Yeah, they want you to prove the sine rule. This is a question that shows up in grade 11. I'm actually shocked that it showed up in a grade 12 paper. But yeah, there's a proof to this. Here's the thing about it. And with this proof, well, with most high school proofs, it's not really things that you have to study too much. You see the proof once, you see the logic behind it, and you're like, okay, so that's how it works. So with this proof, it's a similar situation. You're going to think about the fact that they have sine angle T. How did they get sine angle T if they didn't use the sine rule? Because we're trying to prove the sine rule, so you can't use the sine rule, okay? So how did they do that? Well, the only way you have sine and then of an angle is if you were using trig ratios, which you can only use when you have a right angle triangle, okay? Right now, this is not a right angle triangle. You cannot say, oh, maybe that's 90 degrees. No one told us it's 90 degrees, so we can't assume that. So what we're going to do is we're going to construct a line. Okay, so from R and down here, I'm going to call this Q because, RTP. Might as well just say Q. I wanted to call it M, but then I don't want anybody to now think this is the midpoint. This is not the midpoint, okay? It's just a random point there. But here's the thing with this line, okay? Do you see how this is the x-axis? Okay, I'm drawing a line that is parallel to the y-axis, meaning this is a vertical line and it's going to be perpendicular to this line TP. So that's the first thing we do. We draw this and we're going to write down any constructions we have made. Okay, so here it is. So I'm drawing this line RQ such that RQ is perpendicular to TP. Okay, so this is what we have. Of course, this is also 90 degrees. And now, how would we get sine angle T? Well, sine angle T, you're going to focus on angle T. And sine, using SOHCAHTOA, tells us to look at the opposite side over the hypotenuse side. So take the opposite side, which you see it's RQ. Okay, that's RQ that we have over the hypotenuse side, which is P. Okay, so RQ over P, that's what we have. I'm going to say sine angle T is equal to RQ over P. Great. Okay. Now, another thing that I see they have, because you see we have our sine angle t and our p. That's great. Another thing we see that they have is the sine angle p. So let's look at that. Here's angle p over here, right? Angle p is here, and it's sine. So you need to take the opposite side over the hypotenuse. So the opposite side is the RQ over the hypotenuse, which is the t, okay? Right opposite the right angle. So that is RQ over t. So we'll say, and, okay, I'm just doing this separately, and I can see that sine angle P is equal to RQ over T. Okay, now that we have that, do you see something interesting about these two equations? They both have RQ. So why don't we just make RQ the subject here and RQ the subject here, and then see what happens when they are equal to each other? Okay, so we're going to leave RQ. We can cross multiply really. Okay, so just put this over 1 and then cross multiply. Those multiply and those multiply. That gives you RQ is equal to P sine angle T. Okay, same thing on this side. That has a denominator of 1. You cross multiply and you get RQ is equal to T sine angle P. Okay, so this is what we have. And we've got an RQ and an RQ. They're the same thing. They represent the same thing. Okay, it's the same line. So we're just going to equate them. So you can say RQ is equal to RQ. Therefore, we're saying that P sine angle T is equal to T sine angle P. Now we're almost done. Do you see how here in the denominator there's a T, in the denominator there's a P? We want that to happen. Okay, so we need to make sure that the P is in the denominator and so is the T. So you're going to just divide both hand sides by P and T. So we'll divide by P and then T. So I'll just have to say times T as well. So it also divides by T. And then therefore, look at what happens. The P's cancel and then you're just left with sine angle T over T is equal to, and here what would happen, the T's would cancel and you're left with sine angle P over P. And that's how we prove that. Okay, so that is the proof. This is something they usually ask in grade 11. But yeah, now you can see that they can actually ask it here. Moving on to the next question. Okay, question 8.2 says, in the diagram we have D, B, and C are points in the same horizontal plane. Okay, this is probably just probably somebody highlighted, but okay. And then they tell us that AP is a vertical flagpole, and then a rope is tied from A, the top of the flagpole, to C. So this is the rope, okay? And then they tell us that angle BAC is equal to angle BCD. So these two angles are equal. BAC equals BCD. Okay, so these two angles are equal. BAC is equal to angle BCD, this angle over there. I'm just going to make that, more visible. That is theta as well, okay? And then angle BDC is alpha, which we have over here. This one is alpha. And then they tell us that AB is equal to 4 units, which we have. Okay, the question 8.2.1 says, show that the distance between B and C is 4 tan theta. So they're asking for BC, the distance between point B and point C. Okay, how do we find BC? It's part of a right angle triangle. So we can use trig ratios like we did here, okay, in these ones, like sine of that. So let's just see how we can find this using everything we have. We've got an angle here, theta. And do you see that what we need to find is the side that is opposite this angle? So we have opposite. And then the side that we have is 4 units. That's AB. So what is that side in reference to theta? That side is your adjacent side, okay? Because this is your hypotenuse. So that is the opposite and the adjacent side. So if you're using opposite and adjacent, which trig ratio you're going to use? You're going to use tan, okay? Okay, because of SOHCAHTOA, opposite over adjacent. So we're simply going to say tan theta is equal to the opposite side, which was BC, over the adjacent side, which was AB. I mean, you don't even have to do all of that. You can just say BC over, and then AB was 4. Okay. And then finally just find BC, the distance between B and C, that's BC. So get BC alone. You can do this by getting rid of the 4. So you'd multiply both hand sides of the equation by 4. And so finally BC indeed is equal to 4 tan theta. And that is our answer. Moving on to the next question. Okay, last question, 8.2.2 says, hence show that DC equals all of this. Okay, I try not to get distracted by the way that looks. I mean, I will look at them from time to time just to see if we are following the right steps. But essentially, they're asking you find DC. So we're going to focus on DC. Let's look at DC. Okay, you see the triangle it's part of? This triangle, the non-right angle triangle. So this is where you can use things like the sine rule, the cos rule. I would not advise you use the cos rule. Okay, it usually just complicates things depending on what you have. When you usually have like literal angles, the cos rule is nice to use there. But here, we can use the sine rule, okay, because this is not a right angle triangle. So we have DC. How do we find DC? Let's construct a way to find DC. So if I'm using the sine rule here, remember, you're looking for this side DC. You need to ensure that you have the angle opposite DC. So that angle over there. We don't have it, but we can actually find it because you have this angle and you have this angle. You have two other angles in the triangle. You can find that angle, angle B. So we'll start there. And then what else can we use? So because this one is unknown, but you can actually find this one, the next pair that you need to take, the side and the angle that you need to use, they need to be a pair that is already complete. Do you see that in the previous question, we found BC to be 4 tan theta. So this is 4 tan theta right now. You're going to take BC with the angle that lies right opposite this line BC, which is alpha. Okay, so this is complete BC. We have something for it. And then, the side right opposite it. So we're going to just take it like this. I'm looking for DC. So I'll take it as DC over, then you need to say sine of that angle. So we say sine of the angle right opposite that side, DC, which is going to be angle B, which we will find, and then is equal to, and then because I said the side over sine of an angle, I need to stick with the same thing. I need to say side, so I'm taking BC, okay, over sine of the angle that I'm looking for, which is, okay, I have this. So this is sine of angle D, which is alpha. So this is what we are looking for. We need to specifically first find angle B. Okay, so let's find angle B and then we can put that in. So to find angle B, it's just the third angle in a triangle. So you say 180 degrees minus alpha minus theta. That will give you angle B. I shouldn't call it angle B though, because, there's also this part. So let's call it angle DBC, just to be more, precise about that. So that's angle DBC. And this is equal to 180 degrees minus theta minus the alpha. And I'm realizing it's best to put it like this. Minus, okay, if you take theta plus alpha and you say 180 degrees minus both angles, that's going to give you this angle. Here's why I'm putting it like this, because eventually you're still going to have to say that side over sine of, and then 180 degrees minus this, and then we can reduce this, okay, using reductions. So that's the reason I'm leaving it like that instead. Okay, so that angle B, I'm not going to call it that, I'm calling it DBC. So now I can go ahead and fill this in and we can put everything in. So we're going to say, we'll take DC over sine angle DBC, which is simply going to be sine, and we have 180 degrees minus, and this is theta plus alpha, okay, and then is equal to, again, you're going to say BC over sine angle D, so this is BC over, and then sine angle D is simply this angle here, alpha, so that is alpha. And all we have to do, okay, we already have BC. Why did I say BC? So we already have BC. That is 4 tan theta. I'll put that down. So that's 4 tan theta. You can put the actual formula first, okay? So like what I just did here, I simplified. Because I noticed they don't really take note of that too much. But you can, if you want to, write it as BC and go DBC, you can do that first. That's fine. Okay, so this is what I mean. You can do that first and then finally simplify it based on what they're equal to. And so this is what we have. We just need to find the value of DC at the end of the day. Okay, so to get DC alone, you need to get this out of the denominator. So we can simply multiply both hand sides of this equation by that. But I'll start by simplifying it first. So we have DC over, and you see how this is sine 180 degrees minus an angle. In the same way, if this was sine 180 degrees minus A, this would be reduced to sine A, okay? Because 180 degrees minus A is in sine's quadrant. It's positive there. And so, in the same way, this would just be reduced to sine, and then this is our A. This is theta plus alpha, okay, is equal to, and then that, okay, for tan theta over sine alpha. Here, I wouldn't try to change the tan theta because you see, they have tan theta, so let's leave that. Now we need to get rid of this in the denominator. You can simply multiply both hand sides of the equation by this same sine theta plus alpha, and then that would cancel that out. So sine theta plus alpha, and now what we have is these cancel, and you have DC is equal to 4 tan theta, and then multiply by sine theta plus alpha, and then all over sine alpha. Okay, so this is what we have. How do we get this to end up looking like this? Okay, so we have a tan alpha. We actually do have that. There should be a 4 here. Let's see. Okay, let me just bring this down so we can just compare. Okay, so just comparing these two, because we have sine theta outside here, and then this eventually gets tan theta. I'm going to go ahead and expand this. You see, we have sine theta plus alpha. We can use compound angle formulas for this, okay? So the compound angle formula for sine A plus B. So we know that we'll have DC is equal to, and we have 4 tan theta multiplied by, now this becomes two terms, so I'm just going to use brackets. So sine theta cos alpha, and then plus cos theta, and then sine alpha. Okay, so this is what we have. And then this goes all over sine alpha. Okay, let me just remove this so it doesn't, distract. So this is what we have. And with this, there's one way we can look at this where it can actually help to cancel things out. So why don't we take the 4 tan theta and then put it over this and say it's been multiplied to all of this. Let's try rewriting it like this. Okay, because if you write this as a fraction, okay, a single fraction, and then it's multiplying to these two terms. Do you see over here how there's a sine alpha and then it's going to cancel with this sine alpha? Okay, so let's just rewrite this. DC is equal to, we have 4 tan theta over, and then we have sine alpha, and it's multiplying to these. Okay, just change that to a round bracket as well. So DC is equal to, and we're going to FOIL. So first term multiplies with this term, okay, first term. And so all we're just going to have here, there's not much we can really do. Well, the tan theta can still change. Yeah, but I don't really see that changing anything. So I'll just rewrite it as 4 tan theta, okay, and then it's going to multiply to all of these. So the sine theta, the cos alpha, and then all over sine alpha. Okay. Okay, so you see with cos alpha and sine alpha, those can actually go together. Okay, we can actually simplify them together. So here with this, okay, we're going to multiply again to the second one, and then we have positive, okay, because this is a plus, so plus, and then you have 4. Now I want you to see what happens here. When this multiplies with this, do you see that sine alpha and sine alpha would cancel? Because this is in the numerator, this is in the denominator. This is really over 1, okay, at the end of the day. So those cancel, and then all you'll be left with is the 4 tan theta and the cos theta. So 4 tan theta cos theta. Also something we can actually do there. Okay, so remember how there's something we can do with those, right? If you have cos alpha over sine alpha, here's what they equal. Remember how tan, okay, tan A equals sine A over cos A. This will now be equal to, since it's cos over sine, it's going to be equal to 1 over tan alpha. Okay, because if I just said 1 divided by, or 1 over tan alpha, I can actually just express this as, or expand it as 1 divided by, and then tan alpha. Then tan alpha can change into sine alpha over cos alpha, and then you'd be using tip and times. So 1 times, then you tip that. So swap the numerator and its denominator. And so you see how that works out. So that is just equal to 1 over tan alpha. So what happens is when we divide the tan alpha, it's just 1 in the numerator, tan alpha in the denominator. So DC is equal to, the denominator now has a tan alpha, and then the numerator still has the 4 tan theta sine theta. That's what we have there. And then here you have 4 tan theta cos theta. I'm trying to keep the tans there just because of what we have here. Okay, at this point, let me just see. You see that there is a sine theta that is, they clearly took out as a common factor. So I need a sine theta. So I have a sine theta here, but I don't have one here. I'm going to go ahead and expand that. So DC is equal to, I have 4 tan theta sine theta all over tan alpha. And then plus, this is now 4 sine theta. So we're going to write it as sine theta over cos theta, which is multiplying to cos theta. So do you see that these two would just cancel? And so all that we are left with is everything else, and then just the 4 sine theta in the numerator. Okay, so this is what we end up with. Okay, now, do you see that we have two terms? In the first term and in the second term, 4 sine theta is common. So we're going to take that out as a common factor. So DC equals 4 sine theta comes out as a common factor, and then what is left? In the first term, you just took this out. Okay, so if you block those out, what are you left with? You're just left with the tan theta over tan alpha. Okay, so tan theta over tan alpha, and then plus, and then what is left? It's just the same thing. So you multiply 1 to this to get back to that. So we just have plus 1 here. Okay, now we can finally just compare it. Does it look identical? Okay, yes, it does. The only difference is they put the 1 before. So DC is equal to 4 sine theta, and then we have 1 plus, and then this is now tan theta over tan alpha. And that is our answer. Okay, so we've gotten that DC. Okay, so that is it for this question. And that is the last question for question 8. And that concludes it for the trigonometry section of this paper. So the trigonometry section was not that bad. Honestly, it was fine. The Euclid section was also okay. And I'll see how the other sections are, okay? Because remember, I work with these backwards. Okay, and I will see you guys in the Euclid section.